This video demonstrates the ProvSQL system, a Postgres module that adds support for provenance and probability management to this DBMS. We are now within the PSQL command line Postgres client in a database where ProvSQL has been installed. We'll use as an example in this video this personal table that contains names, positions, locations of the personnel of a fictitious intelligence agency, as long as the classification level of the confidentiality of this information. The first step is to transform this regular relational table into a ProvSQL aware table. For this, we are using the add provenance user-defined function. You can now see that an extra ProvSQL column has been added to the table. It contains provenance tokens, which are freshly allocated universally unique identifiers. You can think of them as tuple IDs for now. Let us try a simple query on this table that lists the distinct positions in the personal lists. Even though the ProvSQL column was not mentioned in the query results include such a column here that contains provenance tokens which characterize the provenance of each tuple of the query results. To understand what these tokens encode, we are going to first create a provenance mapping which will be used to assign the name of each person, as a label for each tuple ID. And now we are using this provenance mapping in the evaluation of the provenance in a formula summaring that simply displays the summaring operations used to produce every query result. So for instance here, we obtain analysts in the results because we have a plus between the tuple corresponding to the label Dave and the tuple corresponding to the label Susan, which were both analysts. So we just display the same query, but we now use this formula and provenance UDF to obtain this human-readable annotation. Let us now consider a more complex query. So this query asks for cities with more than one person in the agency. Let us explore, for instance, the provenance of the Paris tuple in the result. And this time we're going to explore it with a UDF, which is view circuit, which is going to give us a PDF visualization of the circuit. So we can see on this visualization that in the provenance term algebra, the provenance for Paris is obtained as a projection of a selection equality of a plus of 3 instances of the times operator for every pair of persons that are in Paris. So we can now use this provenance information to compute useful things. So for instance, we are going to create a provenance mapping on the classification column of the personal table. And we are going to run a query to determine the minimum clearance level needed to determine whether there is one person, there is at least two persons in a given city. So the clearance level for Paris, for instance, so we are using the security UDF for this. The clearance level for Paris is confidential, which means that in order to determine that Paris is indeed in the query results, we are going to look at every pair of persons So for instance, Dave and Magdalene and Nancy and Dave. And we are going to take the minimum over all such pairs of the maximum of the classification of the two persons in the pair. So here, for instance, to know that both Dave and Nancy are in the query results, you need the max of confidential and restricted, which happens to be confidential. And you don't need the highest security clearance level for Magdalene, which is top secret, because Dave and Nancy suffice to know that Paris is in the query result. Let us now look at a non-monotone query. So query with an except operator here. This non-monotone query is computing the cities which have exactly one person. So we can again evaluate the provenance of the formula. We can evaluate the provenance in the formula semi-ring with monos, the formula M semi-ring. And we obtain this human readable visualization of the provenance. That tells you that, for instance, for Paris to be in these query results, you need to have either Dave or Magdalene or Nancy to be in the in the personal table. And you need also to be sure that neither both Dave and Nancy or both Dave and Magdalene or both Magdalene and Nancy are in the query results. To conclude on provenance, we're going to go back to the original monotone query that asks for the cities with more than one person, so this query. And we are going to look at a different kind of provenance, which is where provenance. So we are using the where provenance here user-defined function to determine the where provenance of this query, and the result is here. So this is a textual representation of the where provenance. And so if you look at the New York tuple, for instance, what this representation means is that this New York data value actually comes from two data values in the input personal table. One with from this tuple with this tuple ID, and one from the tuple with this other tuple ID. Let us now move to probabilistic query evaluation. We are going to add a probability to the personal table, and we are going to put some random, arbitrary probability in this column. And we are going to interpret this as a tuple independent database. So we create a provenance mapping on this probability table. And we are going to run queries. So for instance, we can take the non-monotone query of there exists exactly one person in a given city. And we can compute the probability of this of each of the query results using different approaches. So for instance, first using the naive enumeration of all possible worlds. And so we determine that, for instance, the probability that Paris is in the query result is 41%. So here the naive enumeration of all possible worlds is feasible because we only have 7 different tuples, so we only have 2 to the 7 possible worlds. We can also use other methods for computing the probability. So for instance, this method is going to use Monte Carlo sampling with 1000 samples. And we see that the result is an approximate result. Or we can use knowledge compilation to a DDNF using the C2D tool, which obviously compute the exact same result as we had with the naive enumeration of possible worlds. For a slightly more interesting example, let's take a larger database, a larger table. So we have here a table R with an attribute X, an attribute Y, and a probability, an independent probability for each tuple. We are going to turn this table into a provenance aware table, a ProvSQL aware table. We are going to build a provenance mapping. Let us also activate the timing of queries. And now we can, for instance, try to do a join query using the naive enumeration of all possible words. So we wait a bit, but this takes actually quite some time. So maybe let me interrupt this. So we see that in 10 seconds we didn't get results for the naive enumeration of all possible worlds. We can use other approaches for computing the probability of query results. So for instance, we can take Monte Carlo sampling with a number of samples that is enough to obtain a 1% additive error with 95% confidence. This is the result. So again, it's an approximate result due to Monte Carlo sampling. And we obtained it in around 5 seconds. But now we can use a more efficient method. So for instance, the compilation to a DDNNF using the D# tool here. And we obtain the result much more efficiently, the exact computation of the query results in less than 1 second. Thank you for listening to this presentation. So the ProvSQL software is available on GitHub. Feel free to try it.